Hi everyone, I'm Olivia, and today I want to talk about how a star cluster's evolution can be affected if it's at a stable Lagrange point. So clusters are these large group of stars. Oh, okay. They're these large group of stars. They are gravitationally bound, and they're thought to have been born in the same molecular cloud. This would mean they have roughly the same age and chemical composition. NGC 6791 is one of the oldest open star clusters in our Milky Way galaxy. The age of this cluster is 8 gigayear, and this is a very massive cluster. This cluster is along the magnitude of 10 to the third solar masses, and this mass size is usually associated with younger open clusters. Other old open clusters are usually 1 to 2 orders of magnitude smaller than this value. This is a very strange cluster because it has not dispersed yet, because clusters are expected to dissolve over time. This means that mass will decrease over time as a function of evaporation and tidal shocks, so tidal interactions. This leads to the expectation that the initial mass of this cluster would have been much higher in value than we measure today. When we look at the chemistry of this cluster, it's very consistent with the chemistry of stars of similar ages that belong to the bulge. This cluster is very metal rich and alpha enhanced. Looking at the plot, on the x-axis, we have metallicity. On the y-axis, we have alpha abundance. Metallicity and alpha abundance measures the chemical enrichment in stars. We see the field stars of the Milky Way in black, and there are several local clusters of different ages that are in the rainbow colors. These clusters are all within 1 kiloparsec from the solar circle. From this apogee study, we see the position of our cluster NGC 6791 is at a high metallicity and high alpha. This implies a scenario where the cluster was formed in the bulge and migrated outward to its current location near the solar circle. One suggestion for how this cluster came to be is from radial migration, where the cluster lost its mass due to tidal interactions. Mass decreased as it moved with these orbits associated with churning. Churning is a type of radial migration where the star is exchanging individual angular momentum. But we are proposing, sorry, I messed up. Let me go back. So for radial migration, that story, to summarize, is where the cluster is born in the bulge, so it's forming in the bar, and is going to transfer to a spiral arm, which is then going to move it out to its current location. However, that's not what we think is happening. Here, we're proposing a different theory, and that is that this cluster was moving along with the bar as the bar was growing, and it came to reside at a stable Lagrange point. This is also possibly can explain how this cluster was able to survive for so long. We would like to test whether a cluster residing at a stable Lagrange point meets the conditions in which a cluster like NGC 6791 can survive, or if a cluster can even reside at a stable Lagrange point. Lagrange points are the maxima, minima, and saddle points and the potential if we're in a rotating frame. We're choosing that rotating frame based on a type of perturbation. In our case, that perturbation is the bar and the rotation rate of the bar. Looking at the image, I have overlaid the contour map of the Lagrange points on top of the bar of the galaxy NGC 1300. as a note that I feel like I have to say every time, because it's not a picture of our Milky Way galaxy. Um, Lagrange points L1 and L2 that I kind of denoted in blue are our saddle points. They're along the same axis of the bar, and they're at roughly the same radius. L3, which is in green, is our center of the galaxy here, and L4 and L5 in red are our local maxima of the effective potential, and they are typically located at co-rotation. Co-rotation is the radius where stars in the spiral arms are moving at the same speed. So our star cluster, NGC 6791, is consistent with it being at the stable Lagrange point L5, which I've denoted in pink. When we go to the galactocentric frame, we take the sun to be at 0 degrees, the bar to be at negative 25 degrees, and our cluster to be at positive 70 degrees. And I've set up this geometry in our simulations. So I constructed a test particle simulation consisting of 10,000 particles. First, we needed to make sure there weren't any weird numerical effects happening in our simulation. But after we added the bar perturbation, we wanted to investigate what happens to stars at the L5 Lagrange point. And we also needed to figure out the radial limit to our simulated galaxy. So I am interested in what these Lagrangians do in a bar, and a natural space to look at these orbits is in action space. So in lieu of phase-space coordinates, we want to use these action angles to track the orbital changes in the simulated galaxy. The radial action angle maps onto the eccentricity of the star's orbit. The azimuthal action angle maps onto the size of these orbits, and vertical action angle corresponds to the vertical energy of stars. Looking at the columns going from left to right, we have the radial, azimuthal, and vertical action angles. The x-axes on all of these plots are the initial actions, and the y-axes are the final actions. When we look at the top row, like all of the top row, this is our quiet simulations where we're not adding any type of perturbation just to see how these actions are changing, and we see very little change. However, as soon as I had added a bar perturbation to our simulation, we noticed significant changes in these actions, which is what we expected. What I have shown you thus far was us using ring of stars to test the radial limit to numerical scattering when we add stars to the disk. I'm adding a Plummer distribution function, which I have given you the equation for. And we're going to assign these stars initial phase-space coordinates. I'm going to place these stars at L5, where we're going to first put it in a quiet disk, so no perturbation. Then we're going to grow the bar, so we're adding a perturbation. And lastly, we want to slow the bar down to see what happens to these stars. We expect to see these stars trapped in a stable orbit about L5. One thing that we're considering is that these orbits could be short period orbits that George Contopoulos presented in 1978. Lagrange points correlate to orbital stability. Instead of horseshoe orbits, the stars would be in these short period orbits around L5, where the timescale is going to be around 1 million years. L4 and L5 are resonant regions where stars are on stable orbits. These orbits have a very clear pattern. L1 and L2, on the other hand, are unstable, so they're not going to trap stars, these stellar orbits indefinitely. If the cluster is at L5, so that's our theory, if you put at L5, as long as the bar in L5 is moving very slowly, then we think the trapped orbits might just tag along for that radial ride outward. So in the future, we're hoping to use a Muse to do some in-body simulations to do a very similar setup where we're putting stars at L5. And I would like to leave you with some questions that we're hoping this project will answer, or at least help us understand better. And that is, can the cluster withstand the growth of the bar? As the bar is slowing down and that L5 is moving radially outward, are these orbits stable around L5? And does the cluster have significant changes along co-rotation? And I'd like to acknowledge and thank my advisor, Kate Daniel, and my colleague, Amy Smock, for helping me with this project. Thank you.
Very interesting talk. I'm 6791 is what I've worked on for the last couple of years. So can I more that in 6819? So can I ask you to clarify for me? Are you asking that the cluster would be at L5 as L5 moves with the bar slowing down and growing, or are you saying that the cluster formed and then radially migrated and then was at L5 and then moved out?
No, so we're not saying radial migration at all. So what we're saying is that when you're forming this galaxy and you have the bar, the L5 Lagrange point is going to move when that bar is growing. So like, pretend like this is the bar and this is L5. As this is growing, L5 is also moving. So that cluster formed in the bowl, so with the bar, and it was able to be trapped at that Lagrange point. And so it just moved along with the bar. And
so it's at L5, its whole history is the idea there. Okay, interesting, thanks.
Did you check or do you know in the data what is the V5 of those stars of the cluster?
Sorry, can you say that again? What is the... You repeat your question? I couldn't.
Sorry, no, yeah, I was just curious, since it's a very interesting idea. I was just curious if you checked in the data. I was just curious about the data first of the cluster. Do you know the V5 of those stars of the cluster, the azimuthal velocity?
We have not checked the velocities of this. It was mainly of, sorry, let me go back. Sorry to hurt your eyes. So it was mainly based on this idea of when people were, they're assuming radial migration. Radial migration, there's like sets of conditions that stars have to meet in order to even radial migrate. And this cluster, because it was like born around like 4 kiloparsecs, if you're in the galactocentric frame, is currently at like 8 kiloparsec. And radial migration generally doesn't, at least generally, it doesn't move stuff out that far. Typically, it's like 2 kiloparsecs. So it's really strange that, like, maybe radial migration has a hand in it. We're not saying that it's completely wrong, but it can't be the full answer.
Yeah, no, I totally agree with you. Maybe a suggestion would be to check if there's any connection with, a possible, velocity, speed of the bar. So if you look at the azimuthal velocity of those stars, just to know if roughly what is their velocity, just their kinematics. So if there's any connection with how fast is going the bar in our galaxy, so maybe you can connect also kinematically to the Lagrangian point.
Yeah.
So you mentioned that you need the bar to grow slowly enough for this to work, and I assume that's because if the bar grows too fast, the L5 point just moves on and the cluster stays where it is. Have you looked at intermediate ranges where it would drag only part of the stars, and maybe the stars that were further away from the cluster get kind of left behind at different points? And can you try to use that to diagnose if you can actually find like remnants of the cluster kind of left behind it at more inner radii?
Yeah, okay. That's a great question. And that is one of the things we're working on. So basically, our code to slow the bar is currently in process. We're literally running it right now. So I won't be able to, I won't have that code until that testing is done because we had to write the code for that. So yeah, but that is a great point, and we're definitely looking into that to see what is happening and what constraints we can possibly put on that.
Yeah, very nice. I was thinking about Toma. I'm glad you asked that question because I was thinking about the disrupting cluster in the stable point. But the other connection I was thinking was, is Bernard here? Where is he? There we go. So we spent a lot of yesterday afternoon talking about trapping and bars. Way too much time, I think, actually, maybe. I'm not sure we came to an answer, but Vinod's been thinking about this. So I was just suggesting you guys might want to compare notes.
Right now I'm thinking, wow, right?
I can't hear you.
Yeah, these are really interesting results. And I'm also really curious about looking at how resonance from the bars works on disrupting clusters, how much it moves them. Yeah, so really interesting result.
Yeah, I really hope we can talk after this. That's really cool.
The one connection is you've got these beautiful idea and this beautiful simple model, and then Vinod's looking at this in fully self-consistent simulations. So there might be a nice synergy there.